I'm going to revisit some of the climate stuff. The slides, you're going to see a few of the slides that you've seen before that Phil showed, but a little reinforcement is fine because he gave a lot of information in that hour. So, but I will go into a little more detail. A lot of what I'm going to show is based on a lot of work that was done by John Abotsoglu and Catherine Hedgewish from the University of Idaho. I made some slides for this presentation, so really the credit, most of the credit is due to them. I'm going to summarize what the future climate in the Pacific Northwest may look like based on 40 climate scenarios that were generated for this project. As Phil mentioned, these are driven by two representative concentration pathways, one showing rather aggressive emissions and one showing a curtailing of emissions by about 2050. These two RCPs drive 20 global climate models. And these global climate models have a spatial resolution of a little over 1 degree up to nearly 3 degrees. So that's on average over 200 kilometers across a grid cell. So three grid cells gets you from the west coast of Oregon to the Idaho border. So it removes a heck of a lot of detail. So what we've done, the bulk of this project has been focused on statistically downscaling that information to a resolution that's more relevant to impacts assessments. So these 40 scenarios have been downscaled to either 1/24th or 1/16th degree. Both of those data sets are available. John Abotsoglu will talk more about the data sets themselves following my talk. The source for the downscale data are these GCM runs from the Coupled Model Intercomparison Project, Phase 5, or CMIP-5, which is an international coordinated set of global modeling experiments. And there's a lot of experiments in this coordinated project. The ones we're interested in are the ones for the near history and out to 2100. This is a global project that is sponsored by the World Climate Research Program. Independent of us, we're just using the information they provided. Again, as Phil mentioned, there are 4 representative concentration pathways available to us. We're focusing on 2 of them for the reasons that Phil mentioned, RCP 8.5 and RCP 4.5, expand the range of what seems more plausible. As he mentioned, the lower RCP, which is here is given as 3PD, is sometimes called 2.6, assumes that we will start curtailing emissions within the next 5 years. So that's quite unlikely. The CMIP-5 project has more than 20 global climate models. There's as many as I think an excess of 40 that are involved and have contributed to the CMIP-5 database. We were downscaling daily data and more than just precipitation and temperature. So once we were able to meet our criteria of which models had the data that we were interested at a daily time step, that whittled that number of 40 down to the 20. So that's sort of what drove the selection of these particular 20 GCMs. And the downscaling method is the multivariate adaptive constructed analogs, and John Abotsoglu is going to go a little more into detail about what that means. I'm going to summarize the results and not talk about the individual data sets and how they were created. I'm going to start with climate trends averaged over Pacific Northwest. So I'm just averaging all the grid cells and giving you the general trends for the first half of the remainder of this talk. And then afterwards, I'm going to look at some spatial variability in these changes in climate. So I'm defining the Pacific Northwest as Oregon, Washington, Idaho, and a little bit of Montana. You've seen this slide. This is certainly the most robust change from the scenarios. I just want to spend another minute describing what this slide is showing exactly, the bold line in the center in the historic period and through each of the RCPs, again, is the average from 20 GCMs. And that's the average of the annual change from a baseline. And the baseline I've chosen for this figure is 1950 to 1999, so the average over that 50-year period. And then for each of the model, there's a max and a min, so you're looking at the full range. I've also done something, a little tweak. I've smoothed that data a little bit to make the figure prettier, so it's not so squiggly. Annual changes will actually show a little more variability. I have sort of a 10-year moving window to smooth things out, to bring out the changes more clearly. So that said, the take-home message really here is that by 2030, the scenarios show no annual temperatures that are below the average of what we're used to seeing. The Pacific Northwest world will be dramatically different. And in some cases, especially for RCP 8.5, the temperatures that are simulated here are not just above what we're used to seeing, they're above the maximum temperatures we've seen in the past. So consistently high temperatures, where the forcing from the greenhouse gases is really swamping the natural variability that we're accustomed to. The trends in precipitation relative to natural variability aren't nearly as great. Over the Pacific Northwest, the projections show about a 10% increase in annual precipitation. But the take-home message here is if you take any 10 years out into the future for many of these GCMs, it's very likely that it's going to look like any 10 years that we've experienced over the last 100 years or so. So it's just that it's likelier to be wetter. But if you grab any one particular simulation that you think, and you look at it 10 years in the future and it says things are drying, you're like, why? You might not expect that because there's the general trend. So it's really the trend comes from averaging all the GCMs, not taking any single one. So in addition to precipitation and temperature, which is what much of the downscaled data available is now, either from CMIP 3 or CMIP 5, one of the novel things of this project is we've downscaled other variables, including wind speed. And this is an interesting result and a bit of a surprise, showing a decrease in wind speed over the Pacific Northwest. For RCP, by 2100, the average reduction is a little over, somewhere between 5 and 10%. But some of the models show really dramatic decreases in the average wind speed over the Pacific Northwest, as much as 25%, which would have implications on ET and other things. Now, some variables, if you average over the annual, you really lose some of the signal because there's the sign of that change actually is different between the winter and the summer periods. This is a figure showing the diurnal temperature range. So the average difference between the daily maximum and the daily minimum temperature. On the left, I'm showing the average over the winter, which are the months of December, January, and February. So the diurnal temperature range is projected to decrease by as much as, on average, by about 1 degree Celsius by the end of the 21st century. In the summer, the trend is opposite direction. So the DTR looks to be increasing by about 1 degree. I'm not an ecologist, so I don't know exactly what the implications of 1 degree are, but Dominic tells me it's not insignificant. Another variable we're looking at is we've downscaled is the incoming shortwave radiation that reaches the surface. This is another one of those variables that switches sign in the trend from winter to summer. The projections show a decrease in solar radiation hitting shortwave radiation striking the surface in the wintertime, a decrease of about 5 watts per square meter by the end of the 21st century. And then the trend, again, the opposite in the summer, an increase. Can't quite see the colors about from my angle, but it's about 5 watts per square meter, I think, increase. Mirroring, in a sense, the change in the diurnal temperature range. So these two variables are probably related in what we're seeing. So I've been showing you the average. I've been showing you the range of all the models in these wide bands of colors, but I just wanted to again highlight the fact that if you take any one particular simulation, it's going to take a trace through that band. Here I'm showing MyRock 5 in the blue line, and it's as Phil pointed out, it's a rather representative sort of average projection. And in the summer, in terms of temperature, it's increasing monotonically throughout the 21st century. But if we look at precipitation, you can see that there's quite a bit of to make this figure, I'm using a 30-year window average. So this is highlighting the multi-decadal variability in precipitation. So if you take any decade or 2 or 3 decades out in the future, using a particular run, it might show in around the 2050s, it might show things are getting wetter, but you go out a little further and it might show things getting drier. So that's something to keep in mind when you use an individual simulation from one of these GCMs. Okay, I'm going to switch now and look at some of these spatial patterns because some of the trends are not uniform across the Pacific Northwest, either in magnitude and sometimes even in sign of whether the trend is positive or negative. I'm going to start with temperature. Here's winter daily, the winter daily minimum temperature. As an example, the average, I've taken the 30-year average for the end of the 21st century minus a baseline from 1950 to 2005. The figures I'm going to all show are for RCP 8.5 because they highlight the spatial differences a little better, a little cleaner. On the left, I'm showing the multi-model mean, just highlighting that there's a pretty strong gradient from coast to inland. On the coast, the projected warming is quite a bit less than as we get into the interior. And that's mirrored by the individual MyRock 5 run. In terms of precipitation, there's here I'm showing the multi-model mean for winter and summer. What I wanted to highlight is even though there's a general region-wide trend for a decrease in summer precipitation, it does vary in space, and for the lower part, for northern Nevada, California area and southern Oregon, the trend is actually towards an increasing precipitation, and then as you go north, towards Canada, things get drier. And this next slide is just to compare the multi-model mean to the MyRock 5 sort of representative run. Again, the general trends are similar, but an individual run is going to show more spatial variability. And you can see in the MyRock 5 run, the lower right, lower left, there's actually some areas that are showing drying in the winter, and that's just reflecting the natural variability of the system. Another variable that shows some interesting variability across space is the incoming shortwave radiation. Here I'm showing the winter on the left, summer on the right. In the winter, and this is curious, in the winter there's a gradient, a clear gradient from coast to the interior, east to west, west to east, in the winter time, whereas the summer the gradient becomes north to south. So there's greater increase in shortwave radiation striking the surface in northern Washington than there is in southern Idaho. Okay, so yeah, now here's a repetition of what I just showed in the previous slide. The upper slide showed the multi-model mean again, and the lower is the individual MyRock 5, just as a reference. So in addition to the downscaled CMIP 5 runs, we've also analyzed some regional dynamical downscaling results from a couple projects. Here's an example. I'm showing the North American Regional Climate Change Assessment Program project, which has run a regional model embedded in a global model at a resolution of 50 by 50 kilometers, and then comparing that to some runs we're doing at Oregon State University in conjunction with Oxford University to run a regional model over the western United States at a resolution of 25 by 25 kilometers. And I want to highlight, Phil's already done this, but in case you missed it, I want to highlight the fact that even though we're downscaling models to fine resolution as small as 4 kilometers squared, the driving mechanisms are still coming from a global climate model. So the major east-west trend in spring temperature change, for example, is driven by the GCM. To really get at some of the fine-scale processes and interesting feedbacks that cause the fine-grained differences in trends, we kind of have to rely on, we need to rely on dynamical actual models run at a fine resolution to get some of that, unless we can explicitly incorporate that information into a statistical downscaling approach. And so the interesting patterns here is, as we get to finer and finer resolution, we start to see that the topography matters, elevation matters, and at a high resolution, when we have mountains resolved in the model, we're seeing that at the higher elevations, we're getting more warming at lower elevations. And we're doing some investigation, and it appears to be certainly a snow feedback mechanism is involved. So we're losing snow in the higher elevations, and that's a positive feedback on the warming we're seeing. So in summary, just briefly, the projections show that, not a surprise, temperatures are increasing between 6 degrees Fahrenheit and 11 degrees Fahrenheit by 2100, but a pretty wide range, anywhere between 2 and 15 degrees increase. Wind speeds, interestingly, appear to be decreasing region-wide. I didn't show a spatial map, but it's pretty consistent across the region. Precipitation, diurnal temperature range, and surface solar radiation all show opposite signs depending on whether it's winter or summer. I haven't said much about CMIP3, but we're not seeing large changes between CMIP3 and CMIP5. That suggests that the CMIP3 projections might be rather robust. So whatever work you've done with CMIP3, don't throw it in the trash. There's still a lot. Whatever you learn from it is probably still valid. CMIP5 is a bit warmer. That's in part due to the representative concentration pathways, but it's also part due to the individual models and how sensitive they are to increasing greenhouse gases. Again, future temperatures are consistently above the range of recent past variability, and we're seeing trends in the other climate variables as well, but natural variability is still playing a major factor. So if you just pick any one particular run, look out in the future and ask yourself, what is it saying that, for example, precipitation is going to be in the decade of the 2080s? It's really going to depend on any particular run, and in addition to the forcing that's occurring due to greenhouse gases. And that sums up the climate story. Happy to answer or try to answer any questions. Hopefully John and Catherine can help in if it's too detailed.
David?
Yes.
My question was about you. Oh, this is Kavita Hine with the Portland Water Bureau. I was curious, you guys have talked about the seasonal precipitation changes. Mm-hmm. I'd like to hear how you characterize how extreme precipitation events might change based on these models.
I haven't analyzed the extremes in these downscaled data sets yet myself. I think John has somewhat looked into it. He's nodding his head. Do you want to answer the question, or are you going to? John will answer your question to some extent in his talk.
Tim there, U.S. Fish and Wildlife Service. So the increase in shortwave radiation in the summer is kind of interesting. I'm just trying to work out why more CO2 is causing more sunlight. Is that related to less clouds in the summer?
Yeah.
Okay.
Yeah. I mean, we have a downscaled clouds. I haven't actually looked at the cloud data to see if the GCMs are saying more clouds, but that is certainly the likely reason. Yeah. And that would also explain the increasing diurnal temperature range during the summer. Yeah.
Hey, David.
Yeah.
We have a question from the WebEx chat from Crystal Raymond. Is there an understanding of the mechanisms that cause the regional decrease in wind speeds?
I'm going to leave that to John. John's been looking into that question.
Yeah, I think the regional decrease, this is surface wind speed, by the way. So we've downscaled surface wind speed, 10-meter wind speed. And the mechanism is presumably due to a decrease in the temperature gradients. Most of the winds are set up by temperature gradients. So as temperature gradients decrease, we would expect wind speeds surface wind speeds to decrease. Right. Yeah, horizontal temperature gradient. Horizontal temperature gradient.
Right. So as you go north, the models are showing greater increase in temperature than towards the equator. So that existing gradient that is decreasing. I'm just repeating what you just said. But repetition isn't always bad.
Yeah, hi, Howard Scheller from Fish and Wildlife Service. I have a more simple question, not being a climate modeler, but a user for species vulnerability assessments. These models are sort of characterized now in RCPs. So how do users of this information who previously used things like ensemble models, A1B, A2, is there easy ways to translate? How do these characterizations of these average models fall in with the sort of downscale results from the past, putting it into these somewhat similar pessimistic and optimistic projections from carbon emissions?
Yeah. In some cases, an RCP is not that different from one of the SRES scenarios. Like I think RCP 4.5 isn't too different from B1, is it? So in that case, you can sort of relate those two on some level. Another way might be to, at least for temperature, and some of the other variables might be this way as well. You can instead of looking at the question of how is temperature changing through time, how does it change through accumulated CO2 concentrations? So you can, a figure would be nice, but you can do that if you know for any SRES scenario or compared to an RCP, if you can plot temperature versus increased CO2, it sort of normalizes them, and they all sort of line across the same. They sort of all on top of each other to some extent. It might be easier to have this discussion later, but that's one way of sort of collapsing the different scenarios, getting rid of time, because they all increase. Some just increase faster than others. So if you look at the data instead of through time, but as increasing CO2, they might all collapse. They might to some extent. Yes, Dennis?
We have to do the microphone because we're webcast.
Oh, sorry.
Phil Pasteris with CH2M Hill. You went into detail about the spatial downscaling and the grid size. What was the temporal scale of the GCMs? Was it the monthly time step? Was it the daily, sub-daily? What did you use as your baseline for the model input?
I'm not quite sure. Are you asking at what time step does the model run, or what?
Right. Did you use for your analysis, because there's monthly output, just from the CMIP 5, what did you grab from?
Daily.
Daily?
Yes.
Yeah, so the other thing, back to the discussion on RCPs versus the A1B business and so on, is that for planning purposes, for kind of economic lifetimes, which is 30 or 40 years, they really only start diverging much sort of after that, so it doesn't make quite so much difference. And it certainly is true that if you use the kind of global mean temperature and related to accumulated emissions, the scales do all kind of start lying on top of each other. Yeah. From a practical standpoint, though, unfortunately, the way we've done things is the way of going out to fixed points in time. Yeah. But I think the most important thing is if you're out 30 or 40 years, it's not going to make such a huge difference which of those. They start diverging a lot after that.
Good? Okay.
Just a reminder that if you would rather have a question on index cards, and we can either deal with now or later, that's also an option if you're not so thrilled about speaking at a microphone being recorded.
Well, I will turn things over to John Abascu then if there are no more questions.